Welcome back once again to your physics notes. So for this lecture, we're going to derive the kinematics equations of form velocity versus time graphs. And this is probably one of the more important lectures for this unit in this project. Okay? So when position versus time graphs get complicated, let's start with that. So it's not really complicated, but previously what we've looked at is when objects move at a constant speed. So if I had a position versus time graph, where this is your x dimension, let's say, that would be negative x, this would be t, time, and I said if an object moves at a constant speed, and let's say it starts from some initial position, you would get basically a straight line, it went like that, and the slope of that line would be your velocity, okay? So that's what we talked about so far, but in reality, situations don't have to be like that. You don't have to move at constant speed, and the focus of this project is actually accelerating objects when objects have a constant acceleration. So let's say we have a new example of something that's speeding up at a constant rate from rest. So let's go ahead and just draw our graph. So here's my position graph. Let's say this is x, position measured in the x dimension. Here's time right here. So there's my two axes for my graph. And if I start from rest, I have a starting velocity of 0, and remember the slope of this graph is your velocity, so I would have a starting slope of 0, but I'm speeding up as I go, okay? So I start out with a slope of 0, a second later it increases a tiny little bit, then it increases a little more, 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 and you can see that my slope is increasing over time. So this is definitely not linear, okay? This is not a linear function. Now to me it looks like some kind of quadratic or something like that. I can give you the answer for exactly what that is, and you'll figure that out through experimentation. But what you find is that if instead of plotting the position versus time for this type of motion, I look at velocity versus time, in which the way to do that would be to find this initial slope, which is 0, then the next slope, and then find the next slope, and find the next slope, find the next slope. Find all of these slopes, plot them against the times when they occur. You could make a new graph, and what you'll find for this one is that you do wind up with something linear. Remember, my velocity started from 0, and it's increasing at a constant rate. Okay? So this is now linear. I could write y equals mx plus b. That was t. You can ask yourself right off the bat, what is my slope of this line? Well, using the exact same logic that we used to figure out that velocity is the slope of this graph, it's rise over run. Well, this one would be change in velocity, or rise, over change in run, which is time. So change in velocity over change in time, that is your acceleration. Okay? So you can see that so far we've talked about 3 different properties: displacement, velocity, and acceleration. And now you can see how they're all related. The slope of the position versus time, or displacement versus time graph, is velocity, and then the slope of your velocity versus time graph is your acceleration. Okay? So what you really want to be able to do is go back and forth between all of these graphs, and I could even add a third graph, where now let's graph the third property, acceleration versus time, and what would that look like? Remember, the acceleration is the slope of this line, so you have to ask yourself how I would describe that line. It has a positive slope, and it's constant. So my acceleration should be positive, and it should be constant. So something like this, horizontal line. Okay? So this is an object moving at constant speed, starting from rest. It speeds up, so that graph shows speeding up. This also shows speeding up. It's the exact same motion, but now it's linear. And then here's your acceleration versus time, which tells you the acceleration is not changing, but it has to be accelerating in the positive direction. Okay? So now example 2, slowing down at a constant rate. So we could say, again, position versus time. So this is x. This is t. Now, if I'm slowing down at a constant rate, my starting velocity is positive, and it's high. So I would have at time 0, I would have a high slope something like that, okay? Now, over time, this is decreasing. So I'm drawing just kind of successive slopes that decrease. So you can see, again, this is not linear. The slope of this is my velocity. If I now want to graph velocity of this object versus time, starting out, I'm graphing my slopes now, okay? So I start out with a positive, so it's not 0, it's positive, and it's going to change after a second, okay? And then over here, so starting out, I have a slope that is positive. So I'm going to start out with a positive velocity. Now after that, I have a slightly lesser slope, so it's going to go down a little bit. So here's my next point, and then the next one goes down, and then goes down, and goes down. So the way I drew this graph, it looks like it kind of straightens out over here to where now I have a slope of 0. So I would slow down at a constant rate, and then, let's say, then rest. So then after that, I would have a velocity just of 0. Okay? Now again, the slope of this line is my acceleration. So if I want to plot a graph of acceleration versus time, what I'm actually going to look at is the slope of that line, and how would you describe it? It's constant, it's not changing, but now where this one was positive, this one is negative. So I would have a negative acceleration. But it's constant, it doesn't change. Okay? Now, technically, if you want to be real specific, what I'm showing is this region of the graph. Okay? If I was going to graph this part, I would have an acceleration, okay, because my velocity changed, but I'm not going to graph that part. We'll look at that later. Okay? All right, now, example 3, speeding up from rest and then slowing down to rest. So before I do it, what I suggest you do is in your notes, go ahead and draw this and then sketch what you think this would look like. And a little trick is go ahead and break it into 2 parts. What would speeding up from rest look like? And then what would slowing down to rest look like? Just put those together in 2 parts. And assume that it's doing this at a constant rate, and then it's doing this at a constant rate. So now, what I did here is in this region, you can see my slope is increasing. So it starts at rest, no slope here, and it's speeding up. But then up here, my slope starts to decrease until I come back to rest. Okay? So if I was going to plot velocity versus time, it's going to be a little different than it has before, because I started out with an acceleration in one direction. Now I'm going to have an acceleration in the other direction. So I would start out with a velocity versus time graph. The slope shows me acceleration. So there's the first half of my graph. There's the speeding up part. And now I'm slowing down at a constant rate. So there you go. Now I have an acceleration here, and then I have an acceleration here. You can call those A1, A2 if you want to, but they're 2 different slopes. Okay. So now if I was going to plot acceleration versus time, you can see that this is going to look different than our previous 2, because now we have 2 different accelerations. So I start out with a positive acceleration, and then all of a sudden it changes, and I have a negative acceleration. So you can connect that if you want to. Doesn't really matter, but you have 2 different accelerations. So your graph does change, and you can call this A1, this A2 to correspond with whatever right there. Okay? Now, example 4. So on a test, and on the AP exam, what you should totally be prepared to do is if they give you any kind of situation, they might give you 3 blank graphs. Oh, that's T, that's A. So they might give you 2 graphs that are blank and one that has something filled in. Okay? So let's say I give you some kind of weird graph that looks like this, and then maybe like this, and then maybe like this, and then maybe something like that. Okay? So based on this, can you now fill in the other ones? Okay? So I'm going to start, and I'm actually going to do acceleration first because I think it's easier. If you look at the acceleration, you can see that this slope of this is your acceleration. So I can break these down into A1, A2, A3, and A4. I have 4 different slopes on this graph, okay? So now just plot those. How would you describe A1? A1 is positive, okay, and it's not changing. So I have a positive value that goes on for a little bit until I get to this time right here, and now I have a slope of 0. And then I get to A3. This whole thing, just because it crosses the x-axis, doesn't really change anything. It's still a constant slope right here. So all of A3 is negative and constant. So now I have a negative slope. And then at A4, I bounce back up to 0. So here's my acceleration as a function of time for that velocity as a function of time. Okay? Now the question is, what do these look like? Well, the easy way for me to do it is if you break this up, you can see that for every little bit of time, you are going to cover a little bit more area. Okay? See, these little slices get bigger underneath there. So you can also think back to what this looked like. So that first section is just like that, constant velocity. So it's going to be increasing like that. Okay? That's the first region. Then now I'm moving at a constant velocity. So the tricky part is everybody on here wants to just match that. Remember, constant velocity, the slope of this is your velocity. So here my velocity is increasing as my slope increases, but right there now I just have a region where it stays nice and flat. That's my constant velocity. Okay? Then, now my velocity starts to decrease at a constant rate, and it becomes actually negative. All right? So the slope of this is my velocity, so it's going to decrease and become negative, and then it's going to stay at a negative velocity, which means now I have a negative linear slope, like that. Okay? So this is definitely the tricky one in my mind, but you have a curved section representing acceleration right there. You have a flat section, so I can call this A1, A2, this is A3, and then this section right here is A4, where, I want to be clear, A2 and A4, the acceleration is actually 0, so you can see those are straight lines. A1 and A3, the positive acceleration for A1, so it's curving up, negative acceleration for A3, so it's curving down. Now, this begs the question, and what really comes next is what can we actually do with this information other than just describe graphs of motion? Well, from these, if I take our simplest of equations, let's take take our simplest of graphs. Let's say this is a velocity versus time graph, okay? And let's say the object starts with an initial velocity of v sub 0, okay? And it accelerates at a constant rate, and then sometime later it has some VF, some final velocity. Well, the question is, what can I do with this? Well, it's a linear equation, so right off the bat, we know that we can write an equation to describe this situation, the relationship between these variables. So on the y-axis, we have velocity. So velocity equals the slope of this line, which in this case the slope of a velocity versus time graph. Remember that slope is going to be delta what's on the y-axis over delta what's on the x-axis, which is delta v delta t, which is our acceleration. So our slope is a, and then the x-axis is t, plus your y-intercept, which is normally b, but in this case it's your initial velocity. So what this is this is our first of what we call the kinematics equations. And the kinematics equations are used to predict properties about an object's motion over time. So if we want to know the final velocity of an object or some velocity at a time later, all we need to know is the acceleration, the time we're looking for, and the velocity it started at. This is a very useful equation to predict an object's motion. Now, where else can we look, though? Now, this is something you're not used to doing. This is more of a calculus thing, which you'll do a lot of next year, is there's other places you can look on this graph for information. For example, sometimes I think of graphs kind of like your couch cushions, right? You've got, anytime you go digging in the couch underneath the cushions, you're going to find something interesting. Kind of the same thing with your graph. You can find information not only on the slope, not only on the y-axis, on the x-axis, but also underneath the graph. The area underneath the graph has meaning. Okay? So what is the area underneath that graph? What does it tell us? I'm just going to kind of redraw this. So that's V naught. This is some VF, some velocity later on, okay, which is equal to that right there. So what is this area? Okay. Well, there's a couple different ways you can do this. You can look at this as a trapezoid, and that's a straight line, by the way. You can look at this as a trapezoid and find the area of the trapezoid, or you can look at this as a rectangle with a triangle sitting on top of it. Okay. So if I look at it as a rectangle with a triangle sitting on top of it, the area of this bottom rectangle is going to be the height times the base, which is, remember this is a versus t graph. So this is V naught times whatever this t is, times time. And then the triangle on top is going to be 1/2 times the height times the base, which works out to be 1/2 VF minus V naught times t. Okay, so that's the area of that. Now that begs the question: what is the area? What does that represent? Well, here's what I would do. Let's just look at the units. Okay, so let's look at the units of what's underneath this, and let's just look at the rectangle because it makes the math nice and easy. Okay, when we found the area of that, what we did is we took the height times the base. Well, we'll look at the units. The height has units, meters per second. That's what the units of velocity are. The base has units of seconds. That's what the units of seconds are. And when I find that area, I'm multiplying base times height. So I'm going to multiply meters per second times seconds. Okay? Now think about this. You're multiplying a fraction times another number, so you can put that over 1 if you want to. It makes it easier. But now if you do this, you're going to get meters times seconds over seconds, and you notice that those seconds cancel, which what you get is meters. Now, that may not jump out as interesting, but think about what the units of meters represent. The units of meters equal displacement. I'm recording a video. What do you want? You already ruined it. You might as well ask your question.
Son, they need you with the motor. They got the motor out. They're not sure what to do next. But I'll wait till you're done. I can tell them to wait till you're done.
Yeah, whatever. That's fine. Okay. So the area underneath this curve is your displacement. Now, what is that equal to? Well, I can write an equation. So delta x, or displacement, is going to be equal to the area of the triangle, 1/2 VF plus V naught times t plus V naught t. This is the area of the triangle and the area of the rectangle. Okay? Now, when we're doing this, sometimes you want things to be simplified a little bit. So I'm going to write this in a slightly different way, and it might not make sense right away. Most teachers just give you all these equations, and I'm going to give them to you too. You don't have to memorize them, but I like to show you where they come from. So this one's generally rewritten in terms of acceleration. So the question is, how do we get acceleration into this formula? Well, we know that acceleration is equal to delta v over t, right? Change in velocity over time. Well, change in velocity is vf. Sorry, that should be a minus sign up there, not a plus sign. That's what we had right here. Vf minus initial velocity. So final velocity minus initial velocity. That's your change over time. Okay? Well, you notice I have that same thing right here. Vf minus vt. Vf minus vt. So if I rearrange this equation to solve for that, I can plug it in right there. So Vf minus V naught equals, move this t over, and I get a times t. So if I plug that in for here, up here for the same thing, because it's equal to it, I get delta x equals 1/2 a t squared plus v naught t. So that is a second equation that you will never have to memorize. I'll always give it to you, but it's one of your kinematics equations. Now, so let's go ahead and write what we call the big four equations. So two of them we have already, okay? So Vf equals At plus V naught, where V naught is initial. Change in position, delta x equals 1/2 At squared plus V naught times t. And then now, if I wanted to, you notice that both of these have t in them. You can solve these equations for t and set them equal to each other, and you can get another equation, which I won't make you do this, as far as I won't make you derive it or anything like that, but all that is these are these two equations, but now eliminated t. So you see in this one, I have Vf, V naught, and t. I have no position in this equation. This one, I have position, a, t, and initial velocity. I have no final velocity in this equation. This one I have final, initial, a, and x. There's no time in this equation. Now, we can use this information to solve some practice problems. So, for example, at time t equals 0, these are on your problem set. A car x is traveling with speed v naught. So here's v naught over here. Here's car x. And you can see, even without any other information, this is a velocity versus time graph. So car x, we would describe his speed as constant velocity. Car y starts with 0 velocity and is increasing in speed, so it has an acceleration. Both cars travel on two parallel lanes of the same road. The road is straight. It says the graphs of the speed versus time of the two cars are shown right there. Now, which of the following is true at time t equals 20 seconds? So right there at this time. Car y is behind car x. So it's going to ask me about all these different things. I could start reading them, but what I might as well is look at a couple of things. Remember, the area underneath here equals change in position, right? The slope equals acceleration, okay? So let's use this information to answer these questions. So which of the following true is time t equals 20 seconds? Car y is behind car x. So car y is behind car x. That would be true if car y hasn't gone as far as car x. So look at their areas. There's the area underneath this line all the way down greater than the area underneath this one? And the answer is yes. So that would be true, okay? Now, car y is passing car x. Well, in order for it to be passing, it has to go the same distance and now be going a little faster. And we just said that car y is going to less distance because there's less area underneath the graph. So that's false, so I'm going to cross that one out. Car y is in front of car x. I'm going to cross that out for the exact same reason. Car x is accelerating faster than car y. Well, what is the acceleration of car x? The slope is acceleration, and the slope of this is 0. So the correct answer is the only one that is true, and that's it. Now, from time t equals 0 to t equals 40 seconds, the areas under both curves are equal. So from here to here the whole time, if I find that area and I find that area, I'll get the same thing. Therefore, which of the following is true? So if they're equal now, what's happening? Car y is behind car x. Well, if they're equal, they've gone equal distance, so it's not going to be behind it, it's going to be right next to it. Car y is passing car x. That would be true if car y is going at a greater speed and is right next to it. That's what it means to pass somebody. And if you look at their speeds, car y has a velocity way up here, car x is a velocity right here, so this one is true. Car y is in front of car x. Nope, they've gone the same distance. Car x is accelerating faster than car y, and the answer is no because car x's acceleration is 0. Car y has a positive acceleration. So the answer is B. Okay? So just from knowing that the area is change in position and the slope is acceleration, you can answer those two questions. Now, which of the following pairs of graphs shows the distance traveled versus time and the speed versus time for an object uniformly accelerated from rest? So uniformly accelerated means that its acceleration is constant and it started with an initial velocity of 0. So right off the bat, I have a speed graph. So do all of these start from 0? Let's use that. That'll be the easiest way. That one does, that one does, that one does. So I can't use that. So they all pass that test. Now, uniform acceleration. Well, if I look at a speed versus time, or velocity versus time, uniform acceleration, remember your acceleration is the slope, so I should have a non-changing slope. If my slope changes, I know that can't be the answer. So that one I can cross out, that one I can cross out. I'm now left with these two. So now what I have to look at is the other graph, position as a function of time. And remember, the slope of this tells me my velocity. My starting velocity is 0. So which of these have a slope that starts at 0? Not that one. That slope starts really high and gets smaller. This one starts at 0 and speeds up. So that is my answer.